high voltage seminar. This is the GaNFET's high voltage, high power density and efficiency in PFC and DC-DC design session being presented by Fei Yang. My name is Yichi Zhang, and I will be the moderator for the session. All participants are muted for the session. Please use the chat function to ask a question and address to everyone. We will be answering questions after the webinar. Also chat if you have any problem hearing or seeing the presentation. With that, I will hand it off to Fei to get started.
Thank you, Ichi. Thank you, everyone, for joining this section. Today, I'm going to introduce the TI GaN nitride devices and to guide together with you to see how that can help you to achieve a high power density and high efficiency design in the PFC and DC-DC converters here. So here's the outline of my presentation. First, I will introduce the TI GaN devices, which is engineered for high frequency operation. And from applications point of view, I'm actually going to introduce two applications here, which are demanding for higher frequency and high efficiency and higher power density here. After that, I'm actually going to go to the detailed designs and to see how the TI GaN devices can benefit you in terms of the PFC and DC-DC power converter designs. And lastly, I will show one picture summarizing the reference designs and tools available with TI GaN devices. So with that, I will come to my first slide. As a wide bandgap devices here, the GaN nitride devices actually offers a lot of advantages here. So first of all, with lower CLSS and also lower gate capacitance here, a faster switching speed can be achieved in TI GaN devices here, and that can give you a much lower or reduced switching losses. And that will allow you to push the switching frequency to a much higher value without worrying about the excessive heatings due to the switching losses. Meanwhile, because of the better switching merit or a lower specific on resistance here, the GaN devices will actually have much lower conduction losses given the same die size compared to the silicon counterparts here. In addition to that, when the GaN FET conducts through the reverse conduction, there's actually no body dot here. And since there's no PN junction body dot in reverse conduction, there's no reverse recovery losses as well in the GaN devices. And that again helps to mitigate and reduce the switching losses. At the same time, it can help to mitigate the running and also the EMIs due to your converter operations. So to justify and prove that benefit in terms of lower switching losses, we actually did some experimental tests. So here is actually a comparison based on our experiment data on the double pulse test system. The figure on the left here, it actually shows a hard switching figure merit. So here what we do is we sum first the turn on and turn off losses together in this switching energy, and then we multiply that with the RDS(on) value of the device at 125 degrees C. And we compare the TI GaN devices versus two silicon carbide MOSFET with different voltage ratings here. So all the comparison, they are done at 400 volt buses, and we vary the load current here. If you focus on the green line, which is the TI GaN devices data, first of all, you will notice that the TI GaN devices, the losses will increase linearly with the load current, and the slope here is actually very small. In contrast, if you look at the silicon carbide devices here, first of all, the slope here is actually pretty high compared to TI GaN. And secondly, for the higher voltage silicon carbide devices, it actually also starts to show some quadratic relationships here, as you can see from this blue line. So comparing the TI GaN with silicon carbide devices, you can see a clear lower losses here, especially at the higher current conditions. And that can prove the better figure merit for hard switching conditions. So similarly, we also did that comparison for soft switching converters on the right here in terms of figure merit of the device. So here we basically multiply the turn-off overlap losses with the device's RDS(on) at 125 degrees C. Again, you can see the TI GaN offers a lower figure merit, and which means the losses is much lower compared to silicon carbide devices. And also the turn-off losses here, as you can see, is pretty flat as low current is increased. And that is again benefiting for your soft switching converter designs. So the GaN devices can be available for high frequency operation, but still there are actually a lot of challenges associated with the overall design. So the package parasitic is one of the challenges that will limiting the high frequency operation. So depending on how you place the driver and the GaN devices here, you may end up with different gate loop parasitics, and those parasitics will greatly affect your switching speed. So I will focus on two parasitic components here in a gate loop. The first one is called common source inductance, which is a parasitic inductance in a package that is shared by your gate loop here and also your power loop here. So as you can see from our simulation here, as you have a higher common source inductance value, the switching speed here is actually lowered. And because of that, you will end up with a higher switching losses. So that means with a higher common source inductance, you're not fully utilize maximize the fast switching speed of the GaN nitride devices. On the other hand, if you focus on the total gate loop inductance here, again, we simulated the turn-off cases with different gate loop inductance. Again, you can see that with a higher gate loop inductance, the voltage spike would be much higher with a higher loop inductance, and that will overstress the device's gate. So given a same gate voltage spike here, the gate drive strength has to be limited with a larger power gate loop inductance here. Therefore, the switching loss again will increase. And as you can see, based on this simulation data, your package in the gate loop can actually greatly affect your switching speed. So to deal with the challenges here, in a TI-GaN solution, we actually came up with an integrated solution here where we place the gate driver and the GaN nitride devices in a same package, and we optimize the gate loop here. So by doing that, both the common source inductance and gate loop inductance can be significantly reduced if you compare that with the conventional standard power packages like TO packages, or even with the emerging Kelvin source connected power packages here. So with that, the TI-GaN offers a smaller package with parasitic inductance, and that can help you to push the TI-GaN devices for high frequency operation. So previously we talked about the package integration for high frequency operation. In addition to the integrated gate driver, we actually also make the gate driver in a smart way that we are able to sense the current and temperature of the devices. So by sensing the current of the device, we're able to provide some overcurrent protection and short circuit protection so that we can protect the devices. And by sensing the GaN device's junction temperature, we're able to feed that junction temperature information to the system through a digital signal. And by doing that, the system can actually do some advanced power management controls. And from the package point of view, in addition to the integration of the driver, we also choose this SMD package, which can help you to reduce the power loop parasitic inductance here. And also, we actually provide different packages, both top cool and bottom cool, to provide a thermal design for different applications. Because of the integration and also this low parasitic package design, we are able to achieve a high slew rate up to 150 volt per nanosecond in your real applications. That can really help you to reduce the losses further. In addition, we actually provide some integrated feature where you can adjust the slew rate in a wide range such that you can balance your EMI versus your system's efficiency. Meanwhile, because of this integration, the TI-GaN actually offers a very compact PCB footprint. As you can see from these slides here, we actually combine the TI-GaN half bridge with a discrete GaN half bridge here on the right. So in the TI gain half bridge here, you can see the FET, the driver, the protection, everything is integrated together in this area. And so only some passive components are needed, and you can just provide a 12-volt unregulated power supply to power up the chip. In comparison, if you look at these discrete GaN solutions, you have the GaN devices here, but in addition to that, you also need the external gate driver power supplies and also the gate drivers together to power up the chip and drive the devices. And also it does not have the overcurrent protection feature. And if you really want to implement that, you have to add additional shunt resistor, op amps, and also digital circuits here to achieve a decent overcurrent protection. So as you can see, by comparing the TI GaN half bridge with the discrete GaN half bridge, the TI GaN actually shows a much simplified BOM, and that which is really helpful to reduce the footprint and also to reduce the system BOM cost. In terms of portfolio here, we actually offers different devices with different RDS(on) value and also different packages here. So in our generation 1 devices here, we actually have a much higher RDS(on) in a smaller packages here. And in the Gen 2 devices here, we actually have 2 versions. For the industrial application, we propose these bottom cool devices, which have a much lower RDS(on), and with the bottom cool, it's fitting the industrial applications. For automobile devices here, we actually propose this top cool package design, and that can help you and morph to fit the cold plate design in most of the automobile customer designs here. So here's like one picture summarizing all the features for our generation 2 devices here. So previously we talked about the different packages on bottom cool and top cool. Also we talked about the integrated features for overcurrent and short circuit protection. In addition to that, we also have a new feature called ideal delta mode, and that can help you to reduce the reverse conduction losses during the dead time. In addition to that new feature, in terms of the gate driver integration, we can actually push to 2.2 megahertz in our Gen 2 devices. In terms of slew rate, as I mentioned previously, we can go up to 150 volt per nanosecond, and you can adjust the slew rate by connecting different resistance between the R drive pin to ground. On the power supply side, we actually can accept a pretty wide input on the VDD power supply, which is the only power supply needed to power up the chip here. And once you have that power supply, we can actually also generate a 5 volt, which can be used to power the external digital isolators and also other peripheral circuits. Also, as I mentioned previously, in the Gen 2 devices, we have an advanced feature called real-time junction temperature measurement. So we can measure the device's junction temperature and output as the duty cycle of the digital signal. So by reading that digital signal's duty cycle, you can actively read the device's junction temperature in real time, and that can facilitate you for active power management. So with this part, I will finish the introduction of the TI GaN. So in the following section here, I'm going to introduce 2 applications that are demanding high efficiency and high density designs. So the figure on the top here, it actually shows the circuit diagram for the AC to DC power supply units that are used in data centers, telecom, medical, and industrial applications. So usually in these applications, the power rating of the converter will be below 10 kilowatt. So in these applications, you will have a single phase AC input here, and then through the PFC stage, you will convert AC to a high voltage DC bus voltage here. And then through this isolated DC-DC, you will convert the voltage from a high voltage DC voltage to a low voltage value, which can be applied to different systems. So this power stage is very, very similar to what we observe also on the automobile onboard charger system. So on the onboard charger system, you also have the PFC and the DC-DC stage. The only exception is like, first of all, the power rating would be much higher in OBC systems. it can go up to like 22 kilowatt. And the other difference is like the output of the DC-DC is actually connected to the high voltage on your electric vehicle system. So it could be either 400-volt battery or even an 800-volt battery system. However, if you focus on designs here, it all consists of the PFC and the DC-DC stage. And actually for both these two applications, a higher efficiency and a power density is actually required. First of all, let's focus on the PFC applications for data center and telecom. So in these stages here, in terms of efficiency, in most of the newer designs here, they actually require an efficiency that it would be beyond the 80 plus Cascadian efficiency requirement here. So when we translate that, it actually can end up with a peak efficiency that will go beyond 97%. So that's really a high demand for high efficiency in these applications. Also, in terms of power density, as the data center power supply moves to a higher power, the density is actually also improved here. As you can see, in most of the newer designs here, they require a power density which would go beyond 100 watts per cubic inches. So to reduce magnetic sizes and achieve this high power density, we do need to push the switching speed and push to a higher frequency in this DC-DC and AC to DC PFC applications. At the same time, we also need to maintain a high efficiency at that high operating frequency. And that's where we see the TI GaN devices can fit this application for both high efficiency and high power density. We also see that trend, in the automobile onboard charger system. So in the OBC system, we actually see a great demand for the high power density, which is usually ends up with 3 to 5 kilowatt per liter in some of the newer designs here. Again, to push for higher power density, we do see that the switching frequency on both PFC and DC-DC needs to be increased to achieve that power density, and that again put TI GaN devices in a good position. In addition to high power density, the cost is also needs to be controlled in most of the OBC system. And TI GaN can actually achieve to reduce the system cost by pushing to a higher frequency. So at a high frequency, the magnetic size and volume can actually be reduced, which can help to reduce the passive components cost. And also with the integration of gate driver, we can actually help to reduce the system BOM and can help also to reduce the BOM cost there. In addition, we also need to have a faster release to market and reliability requirement that we see in the OBC system. So to deal with these two requirements, we actually have different reference designs here covering a different power rating and different bus voltages, such that we can provide the customers some available reference designs so in order to provide some guidance for their design. At the same time, focus on reliability, we have done a lot of reliability testing on our devices, both on the component level and also on the application converter level, to make sure the GaN devices in TI is actually designed properly and validated for reliability. So those are the demands that are requiring higher efficiency and higher power density. So in the next few slides here, I will talk about how the TI GaN devices can benefit and achieve a high power density and high efficiency for the PFC designs. So I'm taking a continuous conduction mode totem pole PFC, for example. So in this topology here, the high frequency devices is actually having hard switching losses. And the hard switching losses actually composes of different factors. It have the gate drive losses, the turn on switching losses, the turn off switching losses, and also the daytime losses. And if we go further down, there are actually more components on the turn on. It actually composes of the COSS losses, overlap losses during turn on, and also the reverse current losses. For turn off, we actually have the overlap losses. So those are all your loss components. So with TI-GaN devices, our target is to reduce each of these atoms here such that we can achieve a higher efficiency. Specifically, in GaN devices, the TI-GaN device offers better figure merit, so a lower COSS is achieved here to reduce the COSS loss. Secondly, with the integrated gate drive, we are able to approach the gate drive and push the slew rate to 150 volt per nanosecond. So by doing so, the overlap losses during turn-on can be reduced. Also, as I mentioned previously, there's no body down conduction during reverse conduction in TI-GaN devices. Therefore, there's no reverse recovery losses in TI-GaN devices, so the reverse recovery loss here is 0. And focus on turn-off overlap losses. Again, with the integrated drive, we can actually push the turn-off switching speed to a much faster value. And so by doing that, the overlap losses during turn-off is really small in TI-GaN devices. Focusing on the daytime losses here, we actually proposed and implemented a new feature called ideal diode mode. So in this mode operation, we can actually automatically and adaptively control our daytime such that we can minimize the daytime conduction losses. So by doing so with all these procedures, it can help us to achieve a lower switching losses in TI-GaN devices. This slide here, it compares the TI-GaN devices versus silicon and silicon carbide devices in a PFC. So in the silicon devices here, the dual boost PFC is commonly used here. So in this topology, you have the silicon superjunction MOSFET here used for the boost. And also, you have the boost diode there, which is considering a silicon carbide Schottky diode in these specific conditions. And then for the silicon carbide and TI-GaN based converter designs, we're actually considering this CCM totem pole PFC topology, which can simplify the BOM and reduce the component costs here. So if we focus on the last figure, we're comparing the loss components operating at 1 kilowatt and 100 kilohertz here. So first of all, if you focus on the dual boost superjunction based designs here, as you can see, the conduction losses here is pretty high, and the main reason is at any time in the dual boost PFC, both the silicon superjunction FET and the silicon carbide diode are conducting. And due to the high voltage drop in the silicon carbide diode here, that can end up with very high conduction losses here. At the same time, when the silicon superjunction MOSFET operate at 100 kilohertz, you will see a significant amount of COSS losses, since there's still significant amount of COSS losses in the silicon carbide, in the silicon superjunction MOSFET there. So because of these two factors, the losses is pretty high in the dual boost superjunction based design. And then if you look at the silicon carbide CCM totem pole design here, so first of all, the conducting loss is reduced and COSS loss is reduced. However, there is an additional components introduced here, which is related to the QRR or reverse recovery losses of the body diode in a silicon carbide MOSFET. So because of that, and also because of the higher overlap losses, we do see that it has a much higher overall losses compared to the TI-GaN totem pole CCM design. So based on this comparison, you can see the TI-GaN totem pole CCM PFC can actually offers the lowest losses in the system. And in terms of detailed designs here, in the next few slides, I'm actually going to discuss about some of the design trade-offs that we have, or the design parameters that we have to benefit your design in the PFC with the TI-GaN devices here. So the first parameter that we can control on the CCM PFC is actually the slew rate. So in these three figures, we're actually showing the slew rate of the TI GaN devices under different conditions. And we are comparing them in a buck converter operation at 400 volt. So we're seeing the rising edges here at different slew rate. So in the first cases, you can see when the slew rate is at 150 volt per nanosecond, you do see a very fast transition here. And also the railing here is actually pretty small, and the voltage spike is also very small due to our low package inductance design. And by adjusting that R drive resistance, you can actually slow down, the R drive, and then adjust the slew rate to a lower value. So by doing that, the switching loss will increase, but you have less overshoot, and that is benefiting for your EMI system design. So you do see that the slew rate is one of the parameters you can play with in your PFC design. So the next slide here, it actually shows in terms of losses how the different slew rate would impact the device's losses. So in this condition, we're actually comparing the CCM totem full PFC operating 4 kilowatt and 330 volt RMS AC input and 400 volt bus output. The ambient temperature is 55 degrees C, and the devices here is operating at 200 kilohertz. So in the calculation here, we actually consider both the temperature-dependent conduction loss and temperature-dependent switching losses here, and then we plug that into our thermal model, and then we keep iterating this system until the steady state is achieved. And the figure on the right here, it actually shows the steady state loss components and also the steady state junction temperature of each GaN devices here. So as you can see, from left to right, we're actually adjusting the slew rate from 30 volt per nanosecond to 150 volt per nanosecond. As you can see, by pushing to a higher slew rate here, the loss component is actually greatly reduced here. So more than 38% loss reduction is achieved, and the main reduction part comes from the reduction in the overlap losses here. Because we have a higher slew rate and lower losses, the devices are also much cooler and the system is more efficient. So in addition to the slew rate, there is also a classic trade-off, or I should say, a classic trade-off between your RDSR or conducting losses and your COSS or switching losses here. So in this comparison here, we're actually comparing two devices. One is 30 million, the other is 50 million devices here. And we are comparing the devices operating at different frequency and power levels and giving the same slew rate of 100 volt per nanosecond. So first of all, if we focus on the full power 4 kilowatt design cases, so at full power and maximum ambient temperature here. So this is a condition that we will consider first actually to have a good thermal design for your different devices. So the bar chart here, it actually compares different devices operating at different frequency. So as the frequency goes higher, the losses will be higher. So that will require a more aggressive thermal design. And also you can see that comparing the two different RDSon devices, at full power, the 30 millimeter devices is actually offering much lower losses since the conducting losses is actually kind of dominating in these frequency ranges and these power ranges here. However, as I mentioned previously, the half load efficiency is also very critical for a lot of the PSU designs. Therefore, after we check the thermal condition of the design at full power, we also need to take a look at the half load condition power losses. So on the left figure here, we're actually comparing the 30 million with the 50 millions at different switching frequencies. Again, the power is reduced to half load, which is 2 kilowatt in these cases. So as you can see, at 50 kilohertz, the 30 million devices actually shows smaller losses compared to the 50 million devices. But once the switching frequency goes beyond 100 kilohertz, the 30 million devices actually shows more losses. And the major loss, it comes from the COSS losses here. And so that's a kind of a classic trade-off here between the conducting losses and the switching losses here. So definitely, with TI GaN devices, we do have a variety of different RDSONs and also different package designs, such that you can accommodate different thermal design and also to accommodate and optimize your system based on your operating conditions by selecting a proper RDSON device. So in the next few slides here, I'm actually going to introduce you some of the our reference design examples on the PFC. So the first one actually shows a 4 kilowatt single phase CCM totem pole PFC. And this is actually using our Gen 2 devices here with bottom cool. And the device is actually operating at 50 kilohertz, and that's why a 30 millimeter device is used here. So over the half load ranges here, the peak efficiency is achieved here, and the peak efficiency is beyond 99.2%. In this slide, I'm actually showing another design. So in this design here, it actually has 3-phase interleaved PNC, which can still achieve like 3.3 kilowatt full power. So the interleaved design actually gives you flexibility to control the power and also optimize the losses at light load. So you have the option to turn on all these 3 FETs at light load. However, you can also do phase shading here, which means you turn on 1 or 2 interleaved phases there to help to improve the system efficiency at light load. So this is an experiment data here. So by doing the phase shading, the light load efficiency can be greatly improved here. So here's a summary of the design guidelines for the CCM totem pole PFC with the TI GaN devices. So first of all, TI actually provides different GaN devices with both bottom cool and top cool. So by using different packages, the thermal model can be changed, and that can give you one flexibility for your system design. In addition to that, in terms of electrical performance, you can always adjust the slew rate or choose the proper RDSON to optimize your loss components here. So by doing that, you can always optimize your devices and optimize your converter design in the CCM PFC. So with that, I will actually move to the next section, talking about the TI GaN for the DC-DC converter designs. So in most of the DC-DC converter designs for PLC and also OBC systems in automobile, the soft switching converters are widely used. So here I'm taking a LLC soft switching converter, for example, here, and trying to demonstrate why TI GaN can also benefit for the soft switching DC-DC converters. So there are several reasons here. The first reason is, with a reduced COSS value here, the dead time is actually greatly reduced here with the TI GaN devices. By reducing the dead time, we can actually increase the time for output power delivery, and also at the same time, by reducing the die time, your transformer magnetizing current can also be reduced, which is helpful to reduce the conduction and also the eddy current losses in the transformer design. Secondly, because of the lower gate capacitance in the TI GaN devices, your gate driver losses is also reduced there when they operate at higher frequency. And lastly, because of the lower COSS and lower dead time, you're able to push to the TI GaN devices to a much higher frequency in these soft switching converters. And by doing so, the volume and also the value of the magnetic components can greatly reduced. And that can also enable a further integration of all these magnetic components. So here I'm showing one of our reference designs on the ILC DC-DC stage. So it's a 1 kilowatt ILC design. And here we're actually comparing the transformer sizes of our TI GaN design, which is operating at 1 megahertz, versus a silicon super junction design operating at 100 kilohertz. So first of all, you see there is a significant size reduction in terms of transformer design, and also in terms of volume, you do see a volume reduction from more than 650 grams to less than 100 grams here. So that can prove and kind of validate a high power density design on the DC-DC stage with TI-GaN. In addition to this, PSU applications, we also try to use TI-GaN device to improve the power density for OBC systems, especially on the DC-DC stage here. So here I'm actually showing another example, which is a 6.6 bidirectional onboard charger with TI-GaN devices here. So the topology is the two interleaved PFC on the PFC stage, and on the DC-DC stage, we actually use the Ryzen C/CCC topology for bidirectional power flow. So at both the PFC and DC-DC stage, we're actually increasing the switching frequency, in comparison to a silicon carbide design. As you can see on the PFC stage, by pushing the switching frequency from 65 to 120 kilohertz, the magnetics volume can reduce by more than 25%. On the C/CCC stage here, the silicon carbide design, it has a wide range from 150 to 300 kilohertz. However, once we change that to TI-GaN, our rising frequency can be directly improved to around 500 kilohertz, and we can actually go even higher to 800 kilohertz at light load. And by pushing to a higher frequency, the magnetics volume can actually be reduced by more than 60%. And by pushing to higher frequency again, we can achieve a much higher power density in these OBC designs here. So focusing on the DC-DC stage, so this page actually shows the experimental waveforms of the C/CCC on the OBC system. So it's actually operating around 3.5 kilowatt. So at this point here, we're actually operating at a resonant frequency 500 kilohertz. So if you focus on the waveforms here, we're showing the primary switch-node voltages together with the primary current and also the secondary current here in green. And if you zoom in to the switching trend on the ZVS edges here, as you can see at 400 volt buses on the primary side, we can easily achieve a ZVS within 60 nanoseconds at a load condition of 10 amps here. And that is only achievable, with the TI-GaN's lower CLSS, and that's how it can benefit in the system and pushing for a higher frequency. In addition to that benefit, since we have the top cool devices used for this automobile OBC system, a compact cooling design can actually also help to achieve a high power density. So if you look at our designs here, all the devices and also including the passive components are cooled just from this one single cold plate here. So as you can see from the rear picture here, we have all the 12 GaN devices here, and also the silicon TO package devices for the low frequency FET on your CCM totem for PFC. And also you have the inductor and the transformers, which also have the resonant inductor integrated inside. So all these components together can be cooled by this single cold plate. So I have introduced the different detailed designs regarding PFC and DC-DC. So in addition, to the reference designs and materials are covered in this presentation, we do have some additional resources here, regarding application note focusing on different functions of TI-GaN devices, including like ideal delta mode, third quadrant operation, directed drive, and thermal design. We also have a bunch of training videos that can help the customers and the students to get familiar with the TI-GaN devices. In addition to that, we also have a lot of hardware reference designs and also the half-range boards available that you can directly play with them. And so all those design tools and resources are summarized here, and feel free to visit ti.com/GaN for more information and resources here. So with that, I will conclude my presentation here and take some questions.
Thank you so much, Fei. We do have several questions in the chat window, and everybody else feel free to add more questions to the chat. So one question is, where's the efficiency comparison to silicon carbide coming from? So I assume that the question is asking what type of silicon carbide device you use, like RDS(on) or some other specs you use for the comparison.
Sure. So focusing on this page, I guess that's what the question is about. So for this page we're basically comparing the silicon carbide and TI GaN. So actually, in terms of RDS(on) value, the exact value is actually comparing, is actually a pretty higher RDS(on) devices, since this is only 1 kilowatt. But the way that we compare in terms with silicon carbide is actually when we choose the devices, we choose similar RDS(on). And so, we are doing a real design for the system and then trying to optimize and compare them, especially that's where our condition at 100 kilohertz. So that's the kind of information we have. The detailed RDS(on), I may need to have a double check, but definitely when we compare that, we're trying to do a fair comparison, in terms of loss breakdowns here.
Okay, thank you. And another question is, can you introduce a little more about third quadrant losses in GaN?
Sure.
Like how to calculate and what's the third quadrant losses?
No problem. So third quadrant losses, for example, if you take the total pole PSC, for example, it's mainly happening during the dead time here. So when you have the reverse conduction, based on the data sheet, for either devices, you actually have the third quadrant curves there. So by referring that curve, once you have the current information, you can refer to what's the third quadrant reverse voltages there. So based on voltage and current, you can calculate what's the instantaneous losses there. Definitely that's a function of temperature, but at a given temperature, you can always calculate that losses there. So that's in terms of losses, for the power. But definitely in terms of the real losses, it's also a function of your time here. So on the system, depending on your that time conduction time, you need to multiply that power with the time, so you get the losses, for each switching cycle. And so since that's happening, each switching cycle, eventually you will have to multiply with your switching frequency in order to get the dead time losses. And as I mentioned previously, we actually have an ideal delta mode, which can, help you to reduce the dead time losses. So specifically what we do is, the GaN FET is actually sensing the reverse conduction. So once it senses the reverse conduction, it will actually automatically, implement a synchronous FET operation. So by doing that, you can reduce the switching, you can reduce the reverse conducting losses.
Okay, thank you, Fei. So yeah, thank you so much. I think that concludes this presentation. If you have further questions, please reach out to us. And thanks everyone for joining us. Our session recording and presentation will be available to view later this week on ti.com/high-voltage-seminar. You will also receive email with links to an on-demand presentation and a post-event survey. We would like your feedback so we can continue to improve our content for future seminars. Thank you again. Have a great rest of your day. Thank you.